NewsReader is a research project that built a reading machine to process massive amounts of news in 4 languages. It extracts what happened, who is involved, when and where from the news and stores this information for decades in a central knowledge store using semantic web standards. NewsReader was co-funded by the European Union within the FP7 program. In this presentation, we explain the event modeling component of NewsReader that converts text interpretation to semantic web triples. News is considered as a source of information in which events and entities are mentioned. The same events and entities can be mentioned many times in the same text or across different articles. NewsReader collapses all these mentions into a single unique IDAP representation of the instances, from text to triples or from mentions to instances. You see here the global architecture of NewsReader's reading machine. We start at the top left corner. The text of news articles is processed by a cascade of natural language processing or so-called NLP modules that detect events, entities, and time expressions in text. Each mention in each text is interpreted separately and represented in the so-called natural language annotation format or NAF. When done, the NAF output is stored in a central knowledge store. In the next step, the representations of mentions in NAF are converted to SEM-RDF representations in which these mentions are mapped to unique instances. SEM stands for the Simple Event Model and is a semantic web standard for representing event data. The resulting RDF data is stored in the knowledge store and can be used for semantic search and reasoning. The process described here is called IDAP. We now zoom in to the mapping from NAF XML to SEM-RDF. IDAP stands for Identification, Deduplication, Aggregation, and Perspectivation. First, we determine if two pieces of text are about the same events and entities. If so, we represent them as one instance with pointers to these mentions. Then, information that the mentions share is represented only once, resulting in deduplication. Possibly, sources may complement each other. For example, when new information on an event is published later, this results in aggregation, assuming we can determine that the news is about the same event. Finally, sources may reflect different points of view. We keep track of who said what and model aspects of these viewpoints, resulting in perspectivation of the information given the sources. Let's look at an example. We see here two titles from two news articles published on the same day, 17th of June 2013. One is from Al Arabiya and the other from The Telegraph. Both titles describe exactly the same event, but do this using different words. Qatar Holding and Qatar refer to the same entity, and so do founding families and Porsche family. We can say the same for the event, which is mentioned as sell in one title and as buyback in the other. The natural language processing software of NewsReader detects such entities and events in text. The entities are mapped to DBpedia URIs to identify the instances. DBpedia is the structured database variant of Wikipedia in RDF, with millions of entities and a lot of background data on these entities. There you can find out what company Qatar Holding is, what management it has, and who are the members of the Porsche family. Entities mapped to the same URI will be considered as mentions of the same instance. For the events, this is more difficult, since there is no database in which they are registered. We will show an approach where we use semantic mappings of the complete description of the event to determine their similarity. The final output of the conversion of the mentions to instances and perspectives for the two examples is shown here in this complex graph. The instances are represented according to SEM in the top part. The mentions are represented in the middle as string offsets in NAF, and the perspective is given at the bottom according to the GRASP model. The instances are linked to mentions using the Grounded Annotation Framework or GAF, as represented by GAF denoted by links. We see that the event 2 has GAF denoted by links to buys and sells. The perspective of the sources is represented by prof was attributed to and RDF value links, and is also attached to the mentions. More details on these models can be found in other presentations and the website. Let's consider in more detail the instances in SEM. Instances are defined through unique URIs, unique resource identifiers. In the case of entities, we use as much as possible the DBpedia URIs if available, for example DBpedia Porsche and DBpedia Qatar Investment Authority. These are web references to data points in DBpedia. For events, we cannot find entries in DBpedia. We therefore create a blank URI, which is a unique string that doesn't point to anything. Here it is event 2. Through the mentions to which this instance is linked, we can find the labels for the event. We also model the meaning of the event through other ontologies, such as FrameNet, Commerce Buy, and the Event and Situation Ontology, or ESO, buying. Knowing that the event is an instance of this type, we can interpret the roles of the entities in the event, which are represented by the links between them. From this we can derive who is the buyer, who is the seller, and who owns what when. Entities in NAF are XML elements as shown here for Qatar Holding and Porsche for the two examples side by side. Entity elements have a type attribute, a span element that ultimately resolves to the strings in the text and possibly external references to DBpedia. In this case, the external references are created by DB Spotlight program, which also assigned confidence scores to each alternative. Each string in the text can be classified as an entity, and for each occurrence in the text, the program tries to resolve the reference to DBpedia. Obviously, entities with the same URI can be grouped naturally as mentions for the same instance. The NAF to SEM GRASP program will collect all the entity references in and across NAF files as mentions for the same URI. In this example, we see this will work for Porsche, but not for Qatar, since the best scoring URIs for Qatar are different. Event mentions in NAF are detected by the Semantic role labeling module, for which we show the output of the two examples again side by side. The module creates predicate elements with semantic types as external references for the events and a span that resolves to the strings, here buys and sells. The element contains sub-elements for the different roles. Each role has a type whose value is based on PropBank, but also possibly external references to roles according to other event models such as FrameNet, VerbNet, and ESO. Each role also has a span that resolves to strings. Establishing identity across these structures from two different NAF files is more complicated than for entities. The predicates as strings do not match, but also the semantic types are different. Here the software uses semantic similarity across types to see if they are sufficiently similar. In addition to the events, we also need to map the roles. The module first matches the span of the roles with the span of an entity mention that was extracted in the previous step. If there is sufficient overlap, then the program concludes that it is the entity that plays this role, and we can use the URI to compare the roles across NAF files. In addition, we can also demand that the roles should match, for which we can use either PropBank roles or any of the other semantic roles. If the same entities play different roles, such as being the buyer or seller, we cannot conclude we are dealing with the same event. In this concrete example, we see that there are quite a few mismatches between the role labels and entities. Matching is thus likely to fail. Our matching algorithm for events is based on two further observations. First is that, as we have seen in the examples, identity and similarity are not just based on the predicate or any of the entities involved, but it should be defined as a function of all the components that make up an event. The action process, the participants, their roles, the place, and the time. The sales example makes clear that a difference in one of these components can already imply that we're dealing with different events. So if people talk about sales of 10% between the same participants with the same roles but happening on different dates, this implies that two different events took place, and we can add up the 10% to a total of 20%. The second observation we made is that the information on these components is hardly found in a single sentence, but is usually spread over the text of an article. In the second example given here, we see that the location Malibu Treatment Facility and the date Tuesday are given in the second sentence, whereas the information on the identity of the actress, American Pie actress, and the event itself, Entered, are given in the first sentence. The semantic role labeler detects events with their roles within sentences only, and this will never provide all the information on all the event components that is necessary to establish identity. We therefore split the process in two different steps. First, we aggregate all the event components from different sentences in a single article and create a so-called composite event structure as an instance representation of the event with all the remaining components as SAM relations. To collect these components, we first determine which words refer to the same event or process across sentences. This so-called intra-document coreference set is represented as a layer in NAV. We then collect all the roles of all these events across the sentences and match these roles with entity URIs, time expressions, and places. These composite SAM representations of the event are compared to similar representations extracted from other NAV files. We then check if the components are sufficiently similar. We can tune the way we measure similarity across components in many ways. We can also tune the granularity of similarity by setting a threshold. And we can finally tune the importance of the different components in the software. The program can thus either lump all events together in one big main event or keep every mention of an event separate as a different event. In this picture we show a schematic overview of this same process, where the left and right side graphs represent the event E, participants P, location L, and times T, elements and relations within a single NAV file. Mapping these elements to URIs lumps together information across sentences. Identity within the same document, both for events and across participants, is established through coreference or coref relations between these elements. We gather the data from these NAV files into SAM representations shown in the middle that contain all the components. We treat these SAM representations as composite events to compare them across NAV files. If identity is established, we merge the composite event structures into a new structure with a single unique URI for the event and deduplicate the information they share and further aggregate the information they add. The result of IDAP is an event-centric knowledge graph aggregated over many different sources. In the next slide we show how the result is represented in RDF trig. Entity instances are represented through their URI, mostly obtained from dbpedia, which gives access to more triples for the entities, for instance the URI for Porsche SE. We do not repeat the dbpedia triples in the representations, since they can be obtained elsewhere. Furthermore, we give the list of gov-denoted bylinks to the character offsets in the original sources, where we detected a mention of the entity. We see here references to specific files with the card position in the actual text, marking the beginning and the end of the mention. The labels are given here also as the different expressions that have been used to make reference. The representation of an event instance is very similar, except for the fact that the URI is never pointing to dbpedia or any other external database. Since there is no background knowledge, we provide the ISA links to our ontological classes, of which the event is an instance. For the rest, we see here the labels and pointers to dimensions in the sources, just as we have seen that for entities. The SAM relations are represented as so-called named graphs. In principle, a SAM relation is a triple, with the event URI as the subject, the role as the predicate, and the participating entity URI or time as the object. In addition to the basic SAM relations, Many other relations can be given as predicates. Here we only show semi-relations. Each triple can be seen as a statement. Since we want to be able to express properties of these statements, we place them inside a named graph, which means that we assign a unique URI to the statement as a whole. The syntax of the URI is not important, but it is derived from the first document in which the relation was found and the predicate and role identifier in the NUF file. Because we place the SEM relations inside named graphs, we can express perspective and mention relations to the SEM triples. In the example shown here, we can see that attribution properties uncertain, negative in the sense of not existing, and future are expressed for the first named graph from the previous slide, and that this statement is attributed to Eric Gottfried. In a similar way, we can specify where it is mentioned in a source and who the owner is of this source. From NUF XML to GRASP RDF, perspectives. We've already seen how perspective relations are modeled as triple relations in this example. We show that the sources of perspectives can be either embedded in the text or the perspective can be attributed to the publisher and or the author of the text. In this example, we see a statement made by Porsche CEO Wiedeking in relation to the market share increase of Porsche. Wiedeking is certain that this will not be the case in the future. However, the confirmation is reported by the Telegraph, and this is attributed to them, where they are certain and state that this has happened. We can say that the source Wiedeking is explicitly embedded in the text, whereas the source, the Telegraph, is implicit and counts as the default. We then implemented a function to derive those perspectives for both the embedded implicit and implicit sources. Starting from the NUF semantic role layer, we defined 150 framelet frames that introduce an explicit source as the syntactic subject. For instance, complaining, attempt dissuasion, agree or refuse to act, reporting, predicting, justifying. We use these frames to determine whether a predicate in the text introduces a source or not. If so, we obtain the source entity URI and we look for framelet roles that mark the message or content that the source reports. Usually these are larger phrases or clauses with roles such as topic, message, content, theme or proposition. Next, we check which events are mentioned within the span of the content phrase. For all the events that occur within this span, we create the embedded perspective relation between the source and the event mention. The perspective values are given by other modules for event mentions. Once we have done this for all the predicates in NUF file, we obtain event mentions for which we derive the perspective values and other mentions of events for which we didn't. All the latter events are attributed to the source of the document, being the author and or the publisher. We show here some real output generated by this module for a single sentence from an English article in the Wikinews dataset. In this sentence, there is an announcement made by General Motors about the filing for bankruptcy. The first triples share the mention of the bankruptcy event as the subject. We generate the label itself of this mention, but also the mention of the source introducing predicate that created the perspective, gov generated by, shown here as a comment for readability. The gov has attribution predicate points to the attribution to object. The properties of the attribution object are then given below as triples. We find here the RDF value, certain, non-future, pos for positive confirmed, and negative sentiment. And we also find the gov was attributed linked to General Motors. Note that the mentions of these events can be mapped to the mentions of the event instances in SAM. And this way we can combine SAM representations of events with perspectives. The perspective layer can be used to get an overview of all perspectives of a particular source. The table you see here shows the events on which we found the perspectives from Wiedeking in our automated data set. We can see that he was mostly certain and positive about things that happened, non-future. This doesn't mean much because this is also the most frequent default value for all data. It is more interesting to analyze events he places in the future, or the ones he negates or is uncertain about. In this schema, we show the process of converting NUF to RDF after the pipeline produces the final NUF. When the final nav files are generated by the pipeline, they are stored in the knowledge store, as shown in the top process. In addition, we start nav to SAM grasp module to derive the IDF interpretation and store this in the knowledge store as well. We created two different implementations, one for batch processing of large volumes of news shown in the middle root of the schema, and one for stream processing shown in the lower root. In the case of batch processing, we store the composite event data for each nav file as binary data on disk. After processing all nav files, we compare subsets of composite events according to predefined criteria. The criteria are used to create different subdirectories in which the binary data is stored. For example, a directory with all composite events that happen on the same day and have the same topic. Next, we only compare events within these subdirectories. After comparing all events to each other and performing the merges, we output the complete result as RDF trig files per subdirectory. The RDF trig files are populated as the final result in the knowledge store. In the case of stream processing, we process the nav files one by one as they come in. We output the composite event data as RDF trig and populate directly the knowledge store with the new data without comparing or merging. We then run a Spark query on the knowledge store to retrieve all events that have similar properties according to the identity criteria and the thresholds we set. We then create OWL same as relations between the identifiers of the new events and the identical old events. The OWL same as relations are stored into the knowledge store as well. At any point, the knowledge store can apply the same as relations and merge the separate SAM representations. Both the batch and stream implementations of the module can be highly parameterized for establishing identity. The code of the nav to SAM grasp module is available as open source according to the Apache license. Details are given on this slide. On this slide, you find the main references to papers on this process.